Hello, it's 1:30, so we will begin this meeting. Welcome to our Oil and Gas Regional Monitoring Program Stakeholder Briefing. Thank you for joining us. My name is Karen Kramer. I'm the Unit Chief for the State Water Board's Oil and Gas Groundwater Monitoring Program. Water Board staff have been collaborating with the United States Geological Survey, the USGS, to implement the Oil and Gas Regional Monitoring Program since 2014. And we've been hosting these public meetings periodically to inform the public on the findings of our program. Next slide, please. All right, here is an overview of our meeting today. We'll first have a short introduction and review the intended meeting outcome, as well as a little bit on the program background. Then the USGS will provide an overview of the regional groundwater studies and a summary of findings from several manuscripts that have been published recently. Links to the full manuscripts are provided in the agenda for this meeting, which was sent out with the emailed announcement. You can also find this information on the State Water Board's Oil and Gas Announcements web page. After the briefing from the USGS, we will take a 15-minute break and then reconvene to answer questions sent in from the public by email. Next slide, please. The intended outcome of this meeting is to provide an opportunity to the public to first learn about recent studies conducted by the USGS for our regional monitoring program. We also want to exchange information, and that includes both information we have collected as well as any information that you, the public, may have on these fields that would add to our scientific knowledge. And finally, we are here to answer questions you may have on the published studies. And we really want to focus on the published studies that the USGS is presenting today. Next slide, please. Okay, for those of you who may not be as familiar with our program, we wanted to provide a brief summary of our program history. Our oil and gas groundwater monitoring program began with public concern about water quality from well stimulation, primarily hydraulic fracturing. This led to the passage of Senate Bill 4 in 2013. Now, Senate Bill 4 set the framework for regulation of oil and gas well stimulation and resulted in addition of Section 10783 to the California Water Code. This section of the Water Code required the State Water Board to establish model criteria that would outline how groundwater monitoring would be conducted on an area-specific level as well as a regional scale. The model criteria was adopted through a public process, which included multiple iterations of stakeholder engagement. Next slide, please. Now, the model criteria describes factors that will be considered in the regional monitoring program. This is an excerpt from the model criteria, and as you can see, factors considered for the regional monitoring program include well stimulation treatments, and other events or activities that have the potential to contaminate groundwater, such as oil and gas well failure or breach. And with that, I would like to turn the floor over to Marina Perez, who will talk to us about meeting logistics.
Thank you, Karen. Welcome and thank you for joining the stakeholder meeting for the Oil and Gas Regional Groundwater Monitoring Program. My name is Marina Perez, and I'm a manager with the State Water Board's Office of Public Participation. I'll be your facilitator for today, and I'll begin by sharing some meeting logistics. This meeting is being held virtually and is being recorded and webcast publicly. This workshop is for informational purposes and no formal action will be taken. Before we start with our meeting logistics, I wanted to take this moment to provide a brief land and EJ acknowledgement. Today, we are hosting this meeting virtually from the traditional territory and homelands of the Maidu, Miwok, and Nisenan people in the modern city of Sacramento. We know that they are still actively working to stabilize their livelihoods and preserve their way of life. We equally honor the groups who have experienced economic, environmental, and social disadvantages as a result of historical marginalization. We know that we are meeting during a very difficult and challenging time. We recognize the impact this global pandemic has had and will have on communities across California. We want to thank each of you for finding a way to join us virtually today. We thank you for your patience and understanding as we move to a 100% virtual meeting space so that we can adapt to the current public health concerns. We're doing our best to make sure that everyone can participate in an effective way and that this time is valuable for you. Some of the guidelines for this meeting, as Karen mentioned, this workshop is planned as a 2-hour meeting. However, we will take a 15-minute break after the presentations and prior to the question and answer period. So if you look at your screen, to ask a question or provide a comment, we ask that you please email your question, your comment to oilandgas@waterboards.ca.gov. In the subject line, if you can please include stakeholder meeting comment, as well as providing your first name, your last name, who you represent, whether it's yourself, another person, or an organization, and your concise question or comment. Today we have staff from the USGS that are presenting today and who will be introduced momentarily. We also have staff working behind the scenes to make sure that we have as few participation bumps as possible. Also, I just want to make you aware that there may be a few maybe a few seconds delay, so please be patient with us. At this moment, I'd like to introduce Matt Landon. Matt is a supervisory hydrologist and program chief of the California Oil, Gas, and Groundwater Projects Group with the U.S. Geological Survey. Matt, take it away.
Well, thanks very much for the introduction, and thanks for everyone for attending today's virtual meeting. We're going to be providing an update on the regional monitoring program and summarizing the results from recently published studies. And today's talk summarizes the work of many people involved in the program. We want to start by providing an overview and update on the status of the program. And this will include summarizing some findings from studies completed in 2018. Then we'll be providing short summaries of results from publications over about the last year, including short presentations by Jan Gillespie, Lindsey Ball, and Pete McMahon on some of these results. Note, as Karen mentioned earlier, we're providing brief summaries today. The full results and terminology used are defined in these manuscripts. And again, you can see the meeting agenda and our websites for links to those manuscripts. And then we'll be wrapping up by summarizing some limitations we've encountered so far and approaches and refinements we are using to address these gaps and limitations, and briefly touching on some plans for upcoming work. The regional monitoring program goal is to evaluate the potential impacts from well stimulation and other oil field operations and sources on groundwater. This is a broad assessment of groundwater quality near oil and gas fields. This perspective recognizes that oil fields are complex places with long histories, and assessments considering all factors are needed. The state determines overall goals and objectives, and the USGS undertakes the scientific work within that framework. The work has a regional focus, broader than local areas around projects that are the focus of regulatory monitoring programs. And an important emphasis is identifying and try to fill gaps in information. For example, a common gap is in the vertical interval between where water wells and oil wells are perforated in this conceptual slide at the bottom, or conceptual figure at the bottom of the slide. We can address this gap by analyzing oil well geophysical logs to help estimate the distribution of fresh and saline water in intervals in between. And in places, we're also installing monitoring wells to collect data from deep aquifers. Initially, we're using wells in our studies, we're using existing wells in our studies across many oil fields, and evaluating factors that may explain water quality using historical and new data collected from existing wells. We're then refining our approaches based upon initial results. For example, the map shows an example of a horizontal gap in information here for the Lost Hills oil field, with gaps in water wells available across the study area. And then we're using various approaches to fill gaps, including analysis of geophysical data and drilling and installing wells. In this case, the regional monitoring program installed monitoring wells at this location to help fill a spatial gap. The program has been conducting studies at statewide to oil field scales. Early analysis done during 2014 through 2016 was done to help contribute to the design of the program. Implementation of the program began in 2016 with studies in specific oil field study areas occurring since then. These oil field study areas can include mapping fresh and brackish groundwater, that is groundwater having salinity or total dissolved solids less than 10,000 milligrams per liter. It also includes oil field water and gas characterization, which helps establish a library of data across the state and oil field study areas for comparison with groundwater. And of course includes groundwater quality monitoring and analysis. Thus far, we're pursuing this work in about 25 different oil field study areas around the state. The map at right shows oil and gas fields in Southern and Central California, where most of the major oil fields are located. As part of the statewide design analysis, a relative prioritization of oil fields for regional monitoring was developed by Tracy Davis and others, based upon available data on vertical proximity of groundwater and oil resources, oil well density, and oil field injection volumes. And the outcome of this analysis was that about 100 oil field areas across the state were considered to be in a relatively high priority category for consideration for regional monitoring. These fields are shown in gold. The locations of study areas to date are shown as highlighted outlines of these fields, with the color corresponding to when work in that particular study area began. Result field study areas and comparisons between different studies areas have been published in addition to the data compiled by the program. And we will touch on major findings from completed studies as we go along today. The recent publications that will be summarized later on in today's talks are from the Lost Hills, North and South Bell Ridge oil field study areas, and the Fruitvale oil field area, some of the fields that are highlighted in blue on this slide. Some key principles of our approach to oil field groundwater studies. We put a lot of emphasis on compiling and analyzing existing data. And some of our products only focus on mining existing sources of information to develop new understanding. We map fresh and brackish groundwater using a combination of existing and newly collected geophysical data. We collect samples of groundwater, oil field water and gas, and other potential source waters for analysis for a wide array of constituents to compare and contrast water chemistry and consider with groundwater and consider that multiple sources and processes can affect groundwater quality. Most importantly, we use multiple lines of evidence to support interpretations of data. This includes evaluating relations of water quality to potential explanatory factors, both human and natural, and identifying gaps in data and understanding. Our interpretive process will indicate when information supports conclusions about sources and processes, and when we can't make clear determinations about sources and processes using available data. And we have been adapting plans to address information gaps and describe additional steps that can be taken as we go along. This approach is necessary because oil fields are very complex places with long histories and many natural, geologic, and anthropogenic activities that can affect groundwater quality. And in the following slides, we're going to look at in some more detail at some of these points, including highlighting some examples of what has been learned from completed studies. Compilation and analysis of available information is central to the program. We have a cooperative agreement with California State University, Sacramento, a group led by David Shimabukuro with the geology department, which has played a lead role in mining oil well records. Data compiled and analyzed include those used in assessing regional groundwater quality and potential explanatory analysis, including factors like well depth and historical chemistry data, oil well density, proximity, age, and type, injection activities or injection volumes, reservoir pressures, well integrity, documented spills and leaks, disposal activities, information on geologic sources of constituents, and hydrologic factors. As part of compiling relevant data, we contact the regional boards and CalGEM and ask for study-specific information we should know about, and offer operators an opportunity to share any data they have that can be weaved into the analysis to make sure that we're touching all of the bases. Large numbers of people are involved in the process of compiling, analyzing, reporting on, and reviewing this information. And if the data are not publicly available already in a digital format, we publish it in USGS data releases. So we're going to take all this compiled information and new data and analyze it to identify factors that are important to understanding water quality and potential risk. And we'll look at some examples of that. An example of using analysis of historical data is determining injection volume water budgets for the Lost Hills, North Bell Ridge, and South Bell Ridge oil fields. This work was done by Pete McMahon and others to help put sample data in context and understand the system. Volumes of injection in fields were determined from annual injection volumes for enhanced oil recovery, which includes water flooding and steam flooding, produced water disposal, and well stimulation treatment from CalGEM records. Here, the size of the pies of the different oil fields is proportional to the volume of injection. Within each pie, we show the proportion of injection for different purposes: gray for enhanced recovery, black for produced water disposal, and red for well stimulation. The results indicate that most injection by far is for enhanced oil recovery, followed by produced water disposal. Well stimulation is a very small fraction of total injection, accounting for less than 0.4% of total injection in all fields. The results also indicate that groundwater pumped from water source wells, which is groundwater outside the fields, is an important source of water injected into some fields, accounting for 29% of injection in Lost Hills during this 2014 through 2017 study period. And historically, it's also been important at times in the South Bell Ridge field. These results on oil field water chemistry are important to understand in analyzing variability in the chemistry of oil field waters, which is critical to evaluate any potential mixing between these waters and groundwater. Let's shift to salinity mapping. Salinity mapping involves determining where groundwater resources having total dissolved solids less than 10,000 milligrams per liter are located near oil fields. However, the distribution of available groundwater sample data collected from water wells and produced water samples collected from oil wells shows substantial gaps. And again, analysis of oil well borehole geophysical logs is being used to help fill these gaps. For example, the figure in the upper right is from the Fruitvale oil field and shows vertical gaps of approximately 2,000 feet between where groundwater and produced water sample data are located. And these gaps were filled by estimating salinity or total dissolved solids from analysis of existing geophysical logs. The resulting three-dimensional models of salinity published by Michael Stevens and others using all of these data highlight spatial patterns of salinity and what controls it. For example, results from the Fruitvale study indicate that salinity structure depends upon depth, recharge, stratigraphy, and faulting. And this helps us understand factors that control the quality of groundwater near oil fields. In other areas, electromagnetic surveys are being used to collect data across large areas and extend understanding of salinity distribution in shallow groundwater between wells. The map on the right shows 4 color-shaded areas in the Central Valley in Kern County, where these helicopter-mounted geophysical surveys have been conducted. Bakersfield is located right here. Lindsey Ball with the USGS is leading these efforts, and later in the talk, you'll hear her summarize results from the Lost Hills and Belridge study area. Salinity mapping results are also being put into three-dimensional visualizations. In the example shown here, results from the Fruitvale study area have been put into a 3D interactive visualization that is available from our website. Users can graphically explore the salinity model generated by the study. More of these visualizations for other study areas are under development and will be available in the future. Let's shift to water sampling. Through March of 2020, we've collected samples from about 330 groundwater sites and nearly 60 oil field sites. In March, we had to stop sampling activities due to the pandemic, but just recently resumed limited sampling. The samples span 14 oil field study areas and some multi-study unit designs. We typically collect 15 to 35 samples per study area, depending upon the size and characteristics of the study area. The data are carefully quality assured using field and laboratory quality assurance and quality control analysis. And the data are made publicly available as USGS data releases from the USGS National Water Information System database and from GeoTracker after report publication. I'll quickly highlight a couple examples of how we use the data and what has been learned from some completed and published water quality analysis. An example of using sample data and multiple lines of evidence comes from a published study in the Los Angeles Basin by Justin Kulongoski and others. High methane concentration occurs in Los Angeles groundwater near oil fields. This was known from some previous reconnaissance work as well as the sampling that we did. And there have been some noted historical examples of methane and other hydrocarbon gases associated with oil sources in Los Angeles, primarily leaking oil field infrastructure or faults. So as part of exploratory work for the program, we sampled 37 monitoring wells at different depths located close to oil fields. These wells were selected from a much larger network of wells in the Los Angeles Basin operated by the Water Replenishment District of Southern California. The result of the effort was that high concentrations of methane were found, but that isotopic, chemical, and spatial patterns in the data were consistent with the methane primarily being the result of naturally occurring microbial processes in aquifers, not oil field sources. The main outcome of this effort is that methane from microbial sources is prevalent in Los Angeles groundwater, particularly in deep groundwater. While this does not preclude methane from oil sources also occurring, these high background levels need to be considered in groundwater quality assessments. And this study illustrates that many lines of evidence need to be assembled and analyzed to assess sources for constituents. Work by Pete McMahon and Peter Berry and others analyzed oil field water and gas samples collected from the Lost Hills, North Belridge, South Belridge, and Fruitvale oil fields. The results of sampling of oil wells, injectate, and ponds indicated large variability in the chemistry of water and gas between oil fields, with depth in individual oil fields and in relation to injection into oil reservoirs. This variability was due to both natural and human processes. The implications of this variability are that a wide range of analytes or chemical constituents is required to determine which are useful for tracing oil field water and gas and potential mixing with groundwater in different settings. Because of the chemical variability in oil field waters, the same tracers will not work in all settings. And we've continued to apply a broad array of constituents in the regional monitoring program as the best opportunity to understand potential relations between oil fields and nearby groundwater. And you'll see some additional examples of those efforts later. Next, we'll shift to summarizing some studies published in the last year. Again, these are brief summaries of a few highlights. Many more details are available in the manuscripts linked here in the meeting announcement and available on these programs' websites. The studies include a study of groundwater quality overlying the Fruitvale oil field, which I will briefly summarize, and studies from the Lost Hills and Belridge oil fields, including analysis of salinity distribution and effects of disposal that Jan Gillespie will describe, salinity mapping using airborne geophysical analysis that Lindsey Ball will describe, and a study of radium and groundwater near all of these fields that Pete McMahon will describe. And then we'll wrap up by, I'll describe results from drilling a deep monitoring site near the Lost Hills oil field. And again, all of the data supporting these studies are also available. Let's start with a summary of groundwater quality results from the Fruitvale oil field, underlying Bakersfield, which underlies Bakersfield. And the results were described in a publication by Mike Wright and others. This aquifer is heavily used for public supply, but directly overlies intensive long-term oil development and injection into the Fruitvale oil field. We analyzed collected groundwater samples and historical water quality and data on potential explanatory factors. The results indicate that groundwater quality in this system is primarily controlled by relatively large amounts of recharge from fresh water from the Kern River, which bisects the oil field. Groundwater quality was generally good because of the fresh recharge. We found only trace levels of thermogenic, that's gas from oil field sources, and water from oil-bearing formations detected in a few wells. Based upon the small number of trace detections, we were not able to discern how gas or water from oil sources reached groundwater. Possible sources or pathways could include minor amounts of movement from underlying oil field sources, such as areas with large amounts of injection and a high density of oil wells, some of which are very old. Effects of historic disposal ponds that were used into the 1960s and which were documented to affect shallow groundwater quality in some studies in the 1960s, and natural water and gas migration processes or sources. Although groundwater quality was generally very good in this study area, we found some indications of differences in water quality over time. In one long screened production well, we found higher concentrations of thermogenic methane, that is again methane derived from oil sources, dissolved petroleum hydrocarbons, and older groundwater when we sampled the well in 2015 under higher pumping conditions. In 2016, when we resampled the well under wetter conditions with lower pumping rates, we found lower concentrations of those constituents and younger groundwater. These results did not occur everywhere, as another well showed no change between 2015 and 2016. However, the results indicate that higher pumping under drier conditions may draw in larger fractions of old deep water, potentially containing gas and water from oil-bearing formations. This may warrant future monitoring and monitoring deeper in the system to determine how much changes in water availability can influence the source and quality of used groundwater, which may vary over time. And now I'd like to introduce Jan Gillespie, who's a geologist with the U.S. Geological Survey and a retired professor of geology at California State University at Bakersfield, who will present the results from the next study. Jan?
Thanks, Matt. There might be a slight pause while I try to take control of the screen, but let me tell you a little bit about what my part of the research involves. I'm mainly looking at salinity trends within the aquifers near the oil fields. And to do that, I'm using geophysical logs from oil wells, primarily the resistivity log. The nice thing about resistivity logs is the log looks at the ability to conduct an electrical current through the aquifer materials. And we all know that currents are the flow of currents, electrical currents is resisted through vadostone, so through air, but electrical currents do pass through water. In fact, they pass through water much more readily, fresh water much more readily than they do through salt water. And that's how we can use these tools to determine electrical resistivity and consequently salinity. There are two aquifers in the study area at Lost Hills Belridge, the Tulare aquifer and the overlying alluvium, and they're separated by the Corcoran clay equivalent. I'm going to try to get the laser pointer back, but if not, I think you can follow along. The groundwater here is fairly poor quality. It's not used for drinking water. Some is used for irrigation and livestock. And we've noticed that the salinity generally increases with depth, as is typical in most natural environments. The map on the left shows in colors and contours the depth to the base of water with salinity that's that is less than 10,000 milligrams per liter. And you can see the red color in the northwestern part of the study area shows areas where the depth to the 10,000 milligram per liter zone is about 500 to 600 feet, so fairly shallow. In other words, a thin layer of fresh to brackish water. If we go over to the eastern part of the study area, east of the Lost Hills field, we can see the purple. And that, in that case, we can see that the depth to 10,000 parts per million is about 1,500 to 1,700 feet, also down in the southeast near South Bell Ridge. The wells that I used to calculate the salinities are shown as blue dots, and you'll notice that most of them are outside the boundaries of the oil fields. The reason for that is that within the North and South Bell Ridge field, the Tulare Formation produces oil, and also in the northern part of Lost Hills. In areas where the Tulare Formation produces oil, it's not possible to calculate salinity because oil resists an electrical current in a similar manner to fresh water. So we use core data, mud log data, and driller log data to determine whether or not we had oil in those zones. So we knew to exclude them from our analysis. Next slide. Along with the oil that's produced in these fields is a lot of water. In some cases, about 15 barrels of water per barrel of oil. Some of this produced water is brackish and comes from the Tulare Formation. Other water is much more saline. It comes from underlying reservoirs such as the marine Echigoan and the diatomites of the Monterey Formation, which the salinity of those waters approaches that of seawater. Historically, we've used ponds, and you can see on the map on the right some blue polygons that show some of the water disposal ponds or sumps in the area. Produced water was put into these ponds and allowed to either evaporate into the atmosphere or infiltrate into the alluvial aquifer above the Corcoran clay equivalent. Some of the water in these ponds were about 5 times higher in salinity than the adjacent groundwater in the aquifer. So we were able to look at wells that were drilled post-infiltration in the ponds to notice that the conductivity values, the resistivity values in the electrical logs had changed. The resistance had become much less in parts of the aquifer that were affected by saline produced water. And you can see the wells that we noticed these effects in by the pink dots shown on the map. Next slide. To look a little bit at what this looks like with depth, there are 3 wells shown in this figure. All of them are on the east flank of South Bell Ridge. The well farthest to the right was drilled in 1970. And the upper part of the well bore, from about 100 feet down to about 400 feet, is the alluvial aquifer. The green layer is the Corcoran clay equivalent. Below that is the Tulare aquifer, the Tulare Formation. The red line that you can see across the well marks the depth to the water table. So above that line, we have no groundwater. Below that line, the top of the groundwater table occurred in 1970. And the curve over here on the right that you see in yellow is the electrical log, the resistivity curve. And I've shaded the electrical log in yellow where it is above 3 ohm meters. So 3 ohm meters is about where we see the type of resistivity associated with 10,000 parts per million total dissolved solids. You can see that above the red line in the vadose zone, there's a lot of yellow in that curve. And that's because we're looking at air. So there's a great deal of resistivity to the electrical current recorded by the log. Below the red line in that well, we can see the yellow fade a little bit. It's not quite as pronounced, but it's still there. The water is still higher than 10,000 parts per million. And we also see that below the Corcoran clay equivalent in this well. This well went down from mechanical problems in 1986, and at that time, the well just to the left of it was drilled to replace it. And you'll notice in that well, the top of the water table in the alluvial aquifer had risen to about 120 feet below ground surface. You see that by the red line. And you'll notice that all the yellow part of the section over on the well on the right has been replaced now with a curve marked by the pink bar that is very low resistivity. We don't see the yellow color on the curve anymore. It's very saline. In fact, it's higher than 10,000 parts per million. In 2012, this well went down, was replaced by the well farthest to the left. And by this time, we can see the top of the water table is at about 80 feet. And again, the section is replaced by very low resistivity saline water. We can also look down right above the Corcoran clay, right above the green zone in the 22K sand and see very low resistivity at that point. Whereas if you look in the previous two wells, we actually had yellow colored resistivity logs in that sand. Next slide. We don't just rely on geophysical logs to determine salinity. We also use monitoring wells where we've actually measured salinity in the alluvial aquifer. These wells are shown as open circles in the map on the right. And the larger the circle, as you can see from the legend on the map, the higher the salinity. So most of these larger circles are occurring in the vicinity of some of these ponds that affect the alluvial aquifer. And using a combination of the geophysical logs from oil wells and the sampling from the monitoring wells, we can determine that some of the ponds' brine plumes have extended out to the northeast of the ponds, at least on the east flank of South Bell Ridge, about 3 miles or so. So we've used two different kinds of data to try to show what's happening in these fields. Next slide. The ponds have been phased out over the years, and instead, the oil industry has turned to disposing of the produced water by injection wells below the Corcoran clay equivalent, so in the Tulare aquifer, which is deeper. And disposal permitting here started mostly in the 1970s, and you can see these wells in the map as the blue X's. These are groundwater disposal or produced water disposal wells. And as we noticed with the ponds, we also, over time, as newer wells were drilled post-injection, we noticed in the pink wells where we can see evidence of saline waters extending along the sands in some areas adjacent to the disposal wells. And again, here we're looking at depths below those depths affected by the ponds. We're looking at depths ranging from about 500 to a little over 1,000 feet. Next slide. Okay, here's our two wells. One was drilled shortly after injection. That's the well on the left. And you can see the green line across the top. That's the top of the Tulare Formation, or the base of the Corcoran clay equivalent. So we're looking at the Tulare aquifer below the alluvial aquifer. And you can see that in the well on the left, which was drilled in 1990, the resistivity shown in yellow that's greater than 3 ohms, shown in yellow, gets more and more saline with depth. In 2012, this well went down and was replaced by the well on the right. And here we can see high resistivity interspersed with areas of low resistivity, where the curve no longer has the yellow shadings. And I've denoted those areas with pink bars on the left side of the curve. These indicate sands that have been invaded by saline produced water from some of the water disposal wells. Now, the effects of this injection, again, are much deeper than that of the ponds. However, in some of these areas, we may see a well, like some of these wells, where we see the evidence of saline water in the deeper Tulare Formation caused by injection disposal. And we can also see evidence of brine above the Corcoran clay in the alluvial aquifer that was caused by sumps. Next slide. Next, I'd like to introduce Lindsey Ball. Dr. Ball is a geophysicist at the USGS office in Denver. And she uses airborne electromagnetic surveys to, in a similar way to my study, in that she looks at the conductivity of electricity from electrical currents generated by a helicopter flight to look at what happens in the very shallow portions of the aquifer. So Lindsey, if you'd like to take control, this may take a little time.
Lindsey, if you're speaking, we can't hear you.
Can you hear me now?
Yes.
Thank you. Sorry about that. I took control too soon. Thanks, Jan, for the transition. I'll be discussing the results from the Airborne Electromagnetic Survey that was flown in 2016 adjacent to the Lost Hills and the Belridge Fields. The survey area focuses on the region that's about 5 kilometers or about 3 miles down gradient of the field perimeters where the fields are developed. In this case, we expect groundwater flow to be primarily from the southwest towards the northeast, so our flight lines are located along that side of the field boundaries. We also have some data shown in the black lines here that were acquired a little bit further down gradient of the oil and gas fields to provide a little bit more context into the hydrogeologic background away from the areas of active development. These data were collected essentially to fill in the gaps in our knowledge of salinity between wells where we can't directly observe salinity through water quality measurements or look at borehole geophysical logs in the way that Jan is. And as she mentioned, this is airborne electromagnetics is used to derive a similar type of data to what she's using for borehole log analysis, electrical resistivity. You can see in the map an example of what some of those results look like. We do have higher spatial coverage because of the way the data are collected than you'll typically get with borehole logs. In this case, we have flight lines about every 300 meters in distance away from the field, and then data point density is about every 40 meters along the flight line. We compile those data into a series of maps or cross sections to look at how patterns change throughout the area. So in this case, you're seeing an example depth slice or just a map of resistivity at a uniform depth below the land surface. In this case, about 6 meters or about 20 feet below the ground. You're also seeing some wells coded by their groundwater salinity observations, saline, which is going to be greater than 10,000 milligrams per liter total dissolved solids, brackish, which we'll define as anything between 3 to 10,000 milligrams per liter, and fresh groundwater is going to be blue, which is anything that is less than 3,000 milligrams per liter in the definitions that we used in our study. In this case, the resistivity is color scaled, so you'll see that relatively low resistivity or conductive features that correlate more closely with salty water are shown in the pinks and reds, and then fresher groundwater and lower salt contents are shown in blue. The recent publication that I'll be describing presented a salinity mapping technique that uses the salinity data from wells, co-located with the resistivity data defined from the airborne electromagnetics to map salinity with respect to probability. The results of that mapping develop essentially 3D models of groundwater salinity that reflect our probability of being in a specific groundwater salinity category. We'd use 3 categories, which are following the same definitions I just outlined: saline, brackish, and fresh, where saline's greater than 10,000 milligrams per liter total dissolved solids, and fresh will be called things that are less than 3,000 milligrams per liter, brackish, anything that falls in between. Those are color-coded as their most probable category in these figures, based on the pink zones being saline, the green zones being brackish, and the blue zones being fresh, with the shading reflecting the relative probability or our confidence or ability to map that using the airborne geophysical data and the wells that we have. So light colors are going to be relatively low confidence, and then dark colors show us higher confidence, more successful mapping techniques. What you can see is that at shallow depths, and in this case, we're going to show a series of maps with different depth slices. This is 6 meters or about 20 feet. The middle map shows you a slightly deeper depth interval of 60 meters, and we're showing a deeper interval still at 120 meters. You can see that the color shading gets lighter as we get further down into depth. And that's basically reflecting increased noise in the data as we look deeper into the geology and we start to lose our ability to map with respect to the noise. Using this technique helps us avoid mapping areas where the data get too noisy to be confidently used. You can also see some example cross sections. This goes from section A to A prime across the front of the Lost Hills field. That's the first section that you see. And then also a section going down gradient of the South Belridge field from D to D prime. That's this lower section. So you can also get a feel for how the distribution of salinity changes with depth using these features. You can also see circles that are color-coded again by that salinity class, where the well screens overlap with either the map intervals or are projected onto the cross sections. So what you can see is that we have a relatively strong correlation between the known salinity at these well points and what we're mapping with the airborne geophysics. And now I'm going to give a relative overview of some of the basic features that we can see using the results of this mapping technique. One thing that we observe is that it's very common to see saltier, more saline water in the alluvial aquifer than the regions below, and that water is relatively common throughout the study area. See some of those areas highlighted on the maps as the relatively shallow or first encountered groundwater, particularly in the northeast of the survey area. And in the deeper parts of the alluvial aquifer, we still see relatively saline and brackish water. You can see the extent of some of those features into the subsurface in the sections. We see that below the Corcoran clay equivalent, which Dan had also mentioned, this is one of the major regional clay units that separates the alluvial aquifer from the Tulare aquifer in this location. Below that clay unit, we tend to see fresher water in the underlying Tulare aquifer. We do see zones of high probability saline groundwater, in some cases located down gradient of historical disposal ponds. Some of those ponds that have larger effects are indicated with the golden arrows that you see on the maps. But it's important to note that we also see high probability saline areas in other parts of the study area that don't have any direct correlations to the oil and gas industry. In this case, you'll see some of the shallow groundwater, particularly in the northeastern part of the survey area, is typically very high in salinity. We see that extending to depth, particularly in the very far northeast. We also see some areas of naturally high salinity, for example, in the diatomite formations in the cores of the anticline, where we have coverage in those areas. Another regional scale feature that we see is a notable transition, especially in the shallow alluvial aquifer, towards relatively fresh groundwater, down gradient of unlined surface water conveyances. So in the map, particularly in the shallowest slice, you can see some of these conveyances indicated in blue, and you can see a relatively sharp transition to these blue freshwater classes. And you can also see that transition in the water quality data observed in wells, where you see fresher groundwater observed. And that extends to depth in the alluvial aquifer. And you can see the location of those conveyances also on the section lines, where you can see an abrupt transition from saline and brackish conditions to relatively fresh conditions. And with that, I'll go ahead and wrap up and transition to Pete McMahon. Pete is a research hydrologist with the U.S. Geological Survey, and he'll be telling us about some of the geochemical results for the same area.
Thanks, Lindsay. Hopefully everyone can hear me. The regional monitoring program analyzed groundwater and oil field water near the Fruitvale, Lost Hills, and South Belridge oil fields for the three most abundant naturally occurring radium isotopes, which are radium-224, 226, and 228. In groundwater, the lowest radium activities occurred near the Fruitvale oil field, which is indicated by the blue symbols in the groundwater panel to the left. Radium activities were quite a bit higher in groundwater near the Lost Hills and South Belridge oil fields, data for which are shown by the orange and red symbols. And the highest radium activities in those two study areas generally occurred in samples that also had the highest salinity. Oil field water had higher radium activities than the corresponding groundwater in each of the three study areas. So you could compare the groundwater and oil field panels in the figure. 18% of the groundwater samples had radium activities greater than the maximum contaminant level, or MCL, for radium in drinking water. And all of those exceedances of the MCL occurred in groundwater near the Lost Hills and South Belridge oil fields. Although it's important to note that none of the groundwater wells that we sampled in those two study areas is actually a drinking water supply well. 3 of the 7 groundwater samples that had radium activities above the MCL occurred in wells located down gradient from unlined ponds that had previously been used to dispose of oil field water. At the time, we sampled those groundwater wells in 2017. Ponds up gradient from one of the 3 wells were still active. And so we were able to collect water samples from those ponds to help us understand radium occurrence in groundwater. And like the other oil field water samples that we collected, oil field water from the ponds had relatively high radium activities, as indicated by the green diamonds to the left. Data from multiple chemical and isotopic tracers indicate that the high radium water in those 3 wells down gradient from the ponds was a mixture of ambient groundwater and about 40 to 45% oil field water from the ponds. Next slide, please. Thank you. But even though the data indicated that pond water mixed with ambient groundwater, radium isotope data indicate that the high radium in those 3 wells down gradient from the ponds was not the same radium that was in the ponds themselves. So the question is, well, how could that be? Geochemical data and modeling indicate that the radium that was originally present in the oil field water that was disposed of in the ponds was removed from that water in the near pond environment by reactions like radium adsorption onto iron and manganese oxide precipitates and radium co-precipitation with the mineral barite. Nevertheless, the saline organic carbon-rich pond water still infiltrated into the aquifer and mixed with ambient groundwater. Water-rock interactions caused by that mixing allowed radium that was naturally occurring on the aquifer sediments to be mobilized into groundwater. And that's the source of that high radium in those 3 wells down gradient from the ponds. Some of the important chemical reactions that occurred in the mixing zone include radium desorption from the sediments that was associated with the high salinity in the mixing zone, and radium release by iron and manganese oxide reduction associated with organic carbon enrichment in the mixing zone. An important take-home message from this study is that the analysis of many constituents and multiple lines of evidence were needed to understand radium occurrence in groundwater. Thanks for your time, and now I'll turn the presentation back over to Matt.
Thanks, Pete. As noted earlier, the Regional Monitoring Program is installing monitoring wells in selected locations where there are critical information gaps about groundwater adjacent to oil fields. In particular, gaps in vertical water level and chemical profiles are common. And this first site drilled by the Regional Monitoring Program is located near the Lost Hills oil field boundary. And was drilled to a depth of about 1,880 feet deep through the full alluvial and Tulare aquifer system that Jan described. And 5 wells were installed at different depths, indicated by the blue dots on this figure. A report by Rhett Everett and others summarized the physical and hydraulic characteristics and salinity profiles from this monitoring site. And full sampling results were not available at the time and will be reported in future publications. Results of water level measurements show vertical differences in water levels. Depth of water is shown across the x-axis of this plot, and depth below land surface is on the y-axis, land surface at the top, greater depths as you go down. And the results of the water level measurements show vertical differences in water levels or pressure that are complex, but indicate potential directions of groundwater flow. So flow gradients are downward from the shallowest well and upward from the deepest well or bottom well, converging in the middle of the Tulare system. This is likely because groundwater pumping further east occurs in the Tulare. The groundwater level data indicate that clay layers in the aquifer, which are indicated to some of the shaded zones on this figure, serve to restrict vertical groundwater flow in this system, which is consistent with some of the results that Jan described earlier. And there are multiple lines of evidence of restrictions across clays at this location, including the differences in water levels between different aquifer layers separated by clays, as is shown on this graph, as well as groundwater levels in different layers respond differently over time. And so these characteristics of the aquifer system can have a large influence on water quality. The results from this site at the boundary of the regional aquifer system with an oil field are being compared to those from other sites near oil fields. As several of the studies presented in today's talks have results concerning groundwater quality adjacent to the Lost Hills and Bell Ridge, North and South Bell Ridge oil fields, we wanted to summarize some results spanning these multiple published studies. In groundwater adjacent to the Lost Hills and Bell Ridge oil fields, results to date show that historic pond disposal is affecting adjacent groundwater based both upon analysis of historical data combined with new data and analysis. Geophysical analysis indicates saline water is primarily shallow, above clay layers, protecting deeper fresh groundwater at the regional scale. In addition, pond disposal water can cause reactions with aquifer sediments that mobilize natural constituents such as radium. Increased salinity occurs near, that is within about a half a mile, of disposal injection sites at depths of injection, which is what Jan Gillespie described. However, there's little data at the depths of injection further away from these sites, further than about a half a mile. Groundwater level and historical pressure profiles indicate that clay layers restrict vertical flow in groundwater aquifers in places. And there are some areas of elevated salinity that occur in the study area that are unrelated to oil field activities or sources. And note that analysis of water quality data overlying the oil field is in the late stages, and an additional report will be available in the future on this topic. I'm going to wrap up today's information meeting by summarizing some more general observations from regional monitoring program studies to date, particularly some limitations we've encountered and some ongoing and additional activities that we anticipate are conducting and anticipate to address gaps and limitations in ongoing studies and in the future. I also want to touch on plans for upcoming study areas. Limitations in data and information we've encountered so far include sparse groundwater wells, particularly deep wells overlying and near many oil fields that limit the amount of data in key areas available to assess groundwater quality near oil fields. Our sampling also spans large study areas, so we usually have a relatively low density of data in any particular area. We often have had limited data on potential source water and gas compositions in oil fields and other potential sources, such as water and gas from non-producing oil and gas bearing zones and other geologic sources, such as marine rocks. There's been limited data on pressure differences between oil and groundwater zones that make it difficult to relate sample chemistry data to physical hydraulic information. Oil fields are, of course, very complex places, and so many potential explanatory factors are often located in the same areas. The outcome of all of this is that in our products, we describe what we find about water quality near oil fields and possible contributing factors, but there are relatively few cases where sources and pathways can be clearly determined. Some of the things we have been and will be doing to address these limitations include, in some cases, drilling and installation of monitoring wells to fill gaps. We see an expanded role for this. Increased use of depth-dependent sampling to get vertical profiles of water chemistry and aquifers. And this helps us get more data and vertical profiles from existing infrastructure. Denser sampling and data around areas of potential risk of releases to groundwater based upon an analysis of available data. And continued efforts to collect samples of potential source waters in oil fields and other sources, including natural, non-producing geologic sources of oil, gas, or salty water. Continued and expanded analysis of pressure gradients between oil producing zones and groundwater, including collecting water levels in monitoring wells near oil fields. some resampling of selected wells using changes over time as a tool in water chemistry, as a tool to evaluate possible sources and processes affecting groundwater quality. An example of that is what I described earlier from the Fruitvale case, where changes over time suggested changes in sources of groundwater to a particular well. Using results of we also want to use results of geophysical analysis to inform areas for additional sampling. And we're conducting many comparative studies between oil fields, summarizing what's learned by comparisons of groundwater quality in areas in different settings and with different characteristics. Essentially, the program is continuing to evolve, and we're not necessarily doing the same things in the same way as we were when we started. A brief note on the people involved in addressing these questions. We have a team of scientists from across the USGS with a wide range of expertise. In some cases, we've brought in expertise onto the team from academia, including Jan Gillespie, who joined USGS after retiring from Cal State Bakersfield. We also work in partnership with several academic institutions that have particular expertise, including Cal State Sacramento with data mining, Oxford University with noble gas analysis of oil field systems, and Duke University expertise in chemistry and isotopes of oil field waters. And I want to thank and acknowledge the contributions of all the people involved. In working with the state and regional board staff, 2 new study areas have been selected to begin work this year. These include the Santa Fe Springs oil field in the Los Angeles basin, and a series of about 9 oil fields in the Bakersfield Arch area of central Kern County, between Bakersfield to the northeast and the Elk Hills area to the southwest. Some of the factors considered in selecting these fields included long histories of dense oil and gas development with overlying used groundwater, and new hydrogeologic settings compared to previous study areas. And these new settings will facilitate comparisons to previously studied areas. You can get more information on the program at both the State Board and USGS websites. The websites include links to the publications discussed today, which again provide more complete results and terminology that was discussed briefly today. And thank you again for attending today's presentation. We really appreciate your continued interest. And with that, we'll go back over to Marina for some additional information before the break.
Thank you, Matt. Now that we've learned a little bit more about the Regional Monitoring Program activities and the upcoming study areas, we'll be transitioning into a 15-minute break. Following the break, we'll have the opportunity to hear from you and answer any questions you may have. Your questions are important to us. So as a reminder, please submit a question or your comment to oilandgas@waterboards.ca.gov. Include stakeholder meeting comment or question in the subject line. And also, please make sure to include your first name, last name, who you represent, whether it's yourself, another person, or an organization, and your concise questions or comments. Questions and comments will be addressed by representatives of the State Water Board and the USGS during this period. At this moment, we will now take a 15-minute break. We'll see you in 15 minutes. Okay, well, I guess we're going to go ahead and rejoin the meeting. Welcome back from your break. We will now begin responding to your questions. My name is Marina Perez, and I will be reading some of the questions that we've received from the public. Our first question comes from Lauren Gentile from Era Energy. The question is, regional basin modeling by the USGS and multi-phase flow dynamics indicate that hydrocarbons and deep brines do not typically migrate to the surface together. Given this scenario, how can gas chemistry serve as a reliable indicator of whether deep brines came naturally from depth versus surface spills? Also, can we please change the slide? Thank you.
I think Pete McMahon was going to answer that question, wasn't it? Pete, are you speaking?
I am here. Yeah, I wasn't sure.
Would you like me to repeat the question, Pete?
No, that's fine.
Okay.
Hopefully I remember it.
Very good.
So differentiating between natural migration of deep brines and brine migration from a source at the land surface, like an unlined pond, is something we did have to deal with in that radium study. And noble gases turned out to be a very useful tool for trying to differentiate between those two sources of brines. In our case, higher salinity groundwater that was affected by the ponds had noble gas signatures that indicated that they had been recently exposed to atmospheric conditions. So the noble gases were essentially equilibrated with air. And so they had those samples had noble gas signatures that were very different from what you'd expect in deep brines that were migrating naturally. So noble gases turned out to be pretty effective for distinguishing between those two sources of brines.
Thank you. Thank you, Pete. Okay, next question. Comparison of groundwater salinity in the area of injection on the east flank of the South Beldridge Field suggests upward vertical brine migration of 300 feet in 20 years. That seems incredibly fast. Does this suggest that there may be a strong component natural upward water flow in the area? This comment is from Julie Glavin from Era Energy.
This is Matt Landon with USGS. I'll try to answer that. The information described in the publications, both primarily from Jan Gillespie, was describing the information that was available, and the salinity anomalies compared to in salinity profiles compared to other parts of the study area were located near these injection disposal areas. So, obviously many things could be happening associated with injections and high pressures. And so what was described was just based upon the evidence at hand. What we know about vertical hydraulic gradients or water level gradients in the aquifer comes from two published sources. First, the profiles of pressures within the aquifer based upon historical formation testing data that was described in Jan's study, which showed profiles and changes in hydraulic pressures across clay layers, but generally pressure gradients, somewhere in the ballpark of hydrostatic pressures, not large increases in pressure or upward gradients. At the nearest multiple well, we've drilled two monitoring sites, multiple well monitoring sites across the aquifer system. The one at Lost Hills, as you saw today, shows groundwater gradients going upward towards the middle of the aquifer and downward from the top. But the results that are in the late stages of publication from the nearby North Bell Ridge and South Bell Ridge multiple well monitoring site show gradients downward all the way from the water table to the bottom of the aquifer system. So at this point, we just don't have any information to suggest that there are large upward natural gradients occurring in the area. Again, we were using the information that we had.
Thank you, Matt. The next question comes from Jeff Young, also from Era Energy. His question is, multiple studies and lines of evidence show that hydrocarbons, including methane and deep paleo seawater, naturally migrate upward, primarily along faults across the basin. This would manifest itself as hits for thermogenic gas, chloride, etc. Also, why were faults not shown or investigated as a possible natural source?
I think this is Pete McMahon, the USGS in Denver.
I'm not exactly sure if this question is about one of the specific studies that we talked about, or it's more just a general question. I will say that where we had spatial data for faults that we could plot on maps, we did so. Although it's possible, there are data out there that we're unaware of that we didn't plot. So we tried to plot fault data when we had them. And we also do try to consider faults where it seems like an important thing to do. In the case of the radium story that I spoke about earlier, where the evidence was pretty compelling that mixing between ambient groundwater and water from ponds was the important process occurring. We paid less attention to faults, but in other situations where faults could be important, we do try to pay attention to those.
Very good. Thank you, Pete. Our next question comes from Mark Engel from the University of Texas, El Paso. His question is, the only explanatory factors in the study were distance and characteristics of the nearest oil well and the number, type, and age of all oil wells within 500 meters. This indicates that no other sources or processes outside of oil and gas development were examined, and that natural deep fluid migration, which are very well documented in the basin, example given Peters et al. 2007, and presence of oil seeps was not considered in the interpretation. What attempts were made to incorporate data on other sources, including upward natural oil brine migration in the study?
Yeah, this is Matt Landon with the USGS. Thanks for that question. We did generally consider deep fluid migration sources and presence of oil and gas fluids that could occur as a result of natural processes. In the analysis, we noted in the Fruitvale paper that natural processes, fluid migration, could explain the occurrences. And so we did not definitively define or describe the mechanism by which thermogenic gas reached a few relatively deep groundwater wells. We didn't have specific information. We looked at the literature, of course, which is general in the area, but we didn't have specific information on occurrence of gas and oil in the local aquifer. But we certainly included in the interpretation and in the manuscript that geologic sources and processes could be a contributor or could explain the results that were observed.
Thank you, Matt. The next question comes from Daniel Siegel from Chevron. The question is, in the Fruitvale study, Wright et al., 2019, the authors argue the statistical differences in TDS values between produced waters and shallow groundwater indicate that mixing the two does not affect groundwater salinity. However, the exact opposite is shown in Figure 6 iodine versus chloride and boron versus chloride, which is an agreement with deep basin fluid flow modeling by Wilson and Garvin and USGS 4D petroleum system modeling showing natural upward flow across much of the basin. Doesn't this suggest that the presence of an oil and gas related signature can be completely natural?
This is Matt Landon with USGS. I can take an initial stab at that. And then if I miss anything, Pete, please chime in.
Okay.
We did see large, contrast between groundwater quality and produced water quality in the fruit veil study area. The plots that I think the question is referring to were plots that combined data from across the whole study area. And there is a east to west gradient or change in the water quality across in the produced water, as well as the groundwater across the area. So there's a misleading aspect to that plot. I mean, the plots were intended to summarize overall chemical patterns in the data, but it lumps all the data from the oil field. And within both the produced water bins and the groundwater bins shown on that plot, there are spatial variations. So by looking at all of the data, not just chloride and iodide or chloride versus boron, our conclusion was that we did not see any definitive evidence in the inorganic chemistry data that indicated mixing of deep oil field sources in with groundwater. Pete, anything you want to add there?
Thanks, Matt. This is Pete McMahon again. I'll just mention that in the paper, Wright does note that there is some overlap in chloride and boron data for groundwater and oil field water, but he then indicates that for those particular samples that overlap in concentration, they're actually from different parts of the oil field. So that kind of gets back to the point that Matt was talking about, and that data from different parts of the oil field are combined in that study. And where you see overlapping data, you kind of need to dig a little bit more deeply and determine whether the groundwater and oil field water samples are from the same parts of the oil field. And then finally, I'll just note that regarding the last part of the question, whether the modeling doesn't suggest that there's presence of oil and gas signatures from natural processes. I would say that the Wright paper doesn't rule that out. I think, there's still, they don't say that there aren't any natural, he doesn't say that there aren't any natural processes that contributing to water chemistry there.
Thanks very much. Okay, next question is from Tom Merrifield from Chevron. The question is, large variabilities in salinity have been shown to exist by the study outside of areas with historical operations. Doesn't this suggest that other mechanisms such as natural upwells of brines exist in this area? And what work has been done to investigate natural sources of brines? Sorry.
Lindsey, were you going to initially answer this? Do you want me to?
Lindsey, I think you're on mute.
I think I am on mute. I'm sorry. Could you repeat the question?
Sure. The question is from Tom Merrifield from Chevron. His question is, large variabilities in salinity have been shown to exist by the study outside of areas with historical oil operations. Doesn't this suggest that other mechanisms such as natural upwells of brines exist in this area, and work has been done to investigate natural sources of brines?
So yes, I think he's correct. The salinity patterns do suggest that there are processes at play that are beyond historical oil field operations, and that a number of things probably contribute to the high salinity in this part of the San Joaquin Valley, whether that's upwelling or evapoconcentration, naturally high salinity in soils, which have been mapped in the area as having high salt content. The work that we did with the Airborne EM to date has been basically to just map those salinity patterns without necessarily attributing specific causes to specific locations. While in some places things correlate to historical activities or mostly undeveloped natural rangeland, determining definitive causes, I think, would be a call for additional data like additional geochemical analyses to look at multiple lines of evidence besides just salinity or resistivity. Matt, I didn't know if there's anything you want to say to follow up on that.
Just very briefly, this is Matt Landon with USGS. Yeah, I mean, there are historical literature talking about some of the mechanisms that can cause high salinity in shallow groundwater, evapo-concentrating processes. So that's a source that's well understood. As Lindsey noted, it was some in the airborne surveys, high salinity in the diatomite was available or could be seen in places. So definitely are natural sources of salinity out there. And, that was highlighted in the study that we're aware of those other sources.
Thanks, Matt. Thanks, Lindsey. Okay, our next question comes from Tom Snowden from Era Energy. His question is, in the figures, faults are only drawn within oil and gas fields. Are there other faults outside of these areas that may also be relevant as a potential source of natural upwelling of oil and brines, especially with respect to allowing flow into well BG7?
Hi, this is Pete McMahon again. I'll address this question. There probably are faults outside of the oil field boundaries.
And when we have data, spatial data to plot those faults, we do so. With regard to well BG7, I believe Tom is referring to one of the groundwater wells that was impacted by mixing from the unlined disposal pond. And in that case, we can rule out contributions from natural migration of brines using the noble gas data again. The noble gas data in that well look almost exactly like the noble gas data for the pond water itself, and also for noble gas data for air equilibrated water. Noble gas data in naturally migrated brines looks very different from what we saw in well BG7. So in that particular case, there's pretty strong evidence that natural brine migration isn't the process affecting that well.
Thanks, Pete. Our next question comes from Eric Greenwood from California Resources Corporation. His question is, a primary finding of this paper is that radium appears to be leached out of the shallow sediments due to the influx of saline, reducing produced water. This implies that any saline water source, including natural upwelling of brines, would produce a similar result. Wouldn't that mean that the changes in radium isotopes observed are not necessarily indicative of impacts from oil operations?
This is Pete McMahon again. That's a great question. And I think
there are certainly cases where natural brine migration could mobilize radium from aquifer sediments. In fact, we kind of make that point in the conclusion of the paper. In the case of those wells down gradient from the unlined ponds, those 3 wells, again, I refer back to the noble gas data and how different the noble gas data were for those 3 wells compared to what you see in brines. And so I didn't mention earlier, but we have actually measured noble gases in oil field water, produced water from oil wells, to confirm that the noble gases in that type of water look very different from the noble gases that we saw in the wells down gradient from the ponds, and also in the oil field water disposed of in the ponds. And that is because once that water is put in a pond and exposed to the atmosphere, you get noble gas exchange with the atmosphere that changes its composition from what it looked like originally in the subsurface.
Thank you, Pete. Our next question comes from Brennan Ott from Chevron. His question is, what is oil field water and how is it different from formation water that is found at depth both within versus outside of oil and gas development areas? How would one differentiate between oiled field water, apparently related to oil and gas development, and formation water, naturally occurring in this work?
Matt, it looks like that question was assigned
To me, but please jump in if you'd like to add anything. So we're using the term oil field water to include various types of water in oil fields. So it could be produced water, it could be formation water, it could be water in a pond. And so that's kind of a general term for different types of water. When you start talking about specific types of water, then that's another thing. And we recognize that water, there can be water from oil producing formations that has unique chemistry. There can be water from oil bearing formations, where there are trace amounts of oil and gas, but it's not commercially produced water. And those types of oil bearing formations could have unique chemistry as well. And ideally, the best way to distinguish between them is to collect samples and make measurements, which we try to do whenever we can.
Thanks, Pete. Our next we have their comments. We received a few comments that there seems to be a discrepancy between Ball et al. And Gillespie et al.
So this is Lindsey Ball. We're not aware of any direct discrepancies between the two salinity mapping efforts. I think there might be some challenges in conveying the differences in depths at which the two approaches are working. In general, the depth of investigation that we're using in the airborne electromagnetic data, it really never exceeds 300 meters and is typically quite a bit shallower than that. And that varies by the resistivity of the area and then the ability to map the salinity based on that salinity category. So it is a bit variable, but typically Jan's threshold maps fall well below that interval. We do plan on working on a more integrated report that looks at more of the local implications, that puts some of the salinity mapping efforts into more context. I think that might be a little bit clearer in that case. Jan, Matt, feel free to weigh in on that.
Sure, this is Jan. I can say a little bit about that. I think that part of the confusion may result from the fact, as Lindsey mentioned, that I'm actually measuring salinities much deeper in the aquifer. And typically there we see a general increase in salinity with depth in areas that haven't been affected by other activities, such as, especially in the alluvial aquifer, such as perhaps naturally occurring brines due to evaporative pumping in parts of the area or due to ponds, that sort of thing. So we do get a lot of variability, especially in the alluvial aquifer. And then the variability that we see deeper than that, which is mostly what I'm dealing with and not Lindsey, that variability tends to be more a result of disposed water injection wells.
Okay, thank you. So our next question comes from David Chapin from Era Energy. Sorry. What efforts were taken to investigate for geologic structures, for example, faults and deep folds in proximity to the monitoring site?
This is Matt Landon. I can take an initial stab at that. And then if I miss anything, Jan, please chime in. We were basically working closely with Jan on her regional efforts in drilling the multiple well monitoring site. And Jan and Red Everett, the lead author, analyzed nearby data close to the site. And we were using available information from oil well records and regional hydrogeologic reports to assess, nearby geology to the monitoring site. And so that's the information that we have. Jan, I don't know if you want to add anything to that.
Yeah, I think we based a lot of that mainly on structural cross sections and structure maps on the various clay horizons within the Tulare Formation. So we made structure maps on those based on the well data. We didn't have seismic as part of the study. We did use the faults that were available from public data sources, for instance, the CalGEM reports, and any other published reports in the area. But by and large, it was mainly mapping using well log data.
Thank you. The next question also, sorry, my apologies. So the next question comes from David Siegel from Chevron. The question is, in Everett et al. 2020, what evidence do the authors have that variations in pressure in the deepest well are a result of oil and gas activity, as opposed to natural processes tied to deep fluid movements, such as those described in basin flow modeling?
This is Matt Landon. I'll try to take a stab at that. We note in the report that the water level variations over time in the deepest well are different, follow different patterns through time than the wells, overlying wells, else higher up in the aquifer. And so in the report, and fundamentally, we do not know, what the factors are that explain that difference in water levels in the deeper well. You mentioned, both, nearby oil field activities as possible, factors that could influence that. We mentioned other processes, geologic processes. And so we, at this point, do not know what the cause of the different pattern in water levels over time, what the cause of those are in that deepest well at the monitoring site.
Thank you. So the next question is from David Chapin from Era Energy. This question is, regarding image shared showing water elevation changes and communication in Lost Hills near the new water well, the image shows water flowing from alluvium to Tulare, but the report states that the CCE is an effective aquitard between well 4 and 5. The image appears inaccurate.
Yeah, this is Matt Landon. Thanks for that question. And to clarify, the point was that there are big differences in groundwater levels between different aquifer layers separated by clays, and that the potential gradients were downward from the shallow system into the Tulare and upward from the bottom of the system into the middle Tulare. So it's about potential groundwater flow. Incorporating the more regional results from Jan Gillespie's study, vertical head differences were found in some areas, but not in other areas, including further to the east, where the lithologic character of clays can change. So we're not necessarily saying that clays are going to be a barrier everywhere. What we noted and what was in the report and the focus of the figure was that there are downward gradients across the CCE, whether or not there's groundwater flow occurring right at that location versus other locations is we can't know that from just the monitoring site.
Thank you. Our next question comes from Joe Ashley from the California Resources Corporation. His question is, the research notes that every single water sample collected in the study contained at least one volatile organic compound, and that those were largely anthropogenically derived, example given PCE and chloroform, suggesting that other land use activities have had more of an effect on groundwater quality with respect to VOC occurrence than oil field sources. Given how ubiquitous anthropogenic VOCs are at the site, isn't it likely that biodegradation of VOCs unrelated to oil field operations also seems a more likely explanation for the shift observed in, I'm sorry, I can't really read that, 13C DIC than produced water. Sorry, if somebody can help me with that. I am having a hard time reading that portion there.
Yeah, no worries. This is Pete McMahon again.
That's, the Delta 13C.
Delta 13, yes, thank you.
Of the DIC.
Mm-hmm.
That's a really intriguing question. I think this question is being asked about the Fruitvale oil field and where there are a lot of anthropogenic VOCs. But it's unlikely that VOC degradation is affecting the C13 shift, and for two reasons. First of all, the concentrations of dissolved inorganic carbon are about 3 to 4 orders of magnitude higher than the concentrations of VOCs in the groundwater. So any biodegradation of VOCs to CO2 would have a minimal effect on the DIC pool just because there's so little VOC carbon relative to DIC in the system. And secondly, if VOC degradation was occurring, typically during biodegradation, VOC degradation of those kind of compounds produce isotopically light carbon. And so the DIC would be getting more negative in its C13 value. But the shift that we measure shows that the DIC values are getting more positive. So the shift in DIC is opposite of what you'd expect if VOC degradation was important.
Thank you very much. Okay, we've got just a few more questions left. I'm doing a time check. It is 3:23 p.m. We will continue and complete these next 6 questions. So for those of you who have expected to be here until 3:30, we might be done by 3:30, but if not, hold tight. We will continue until we're done. And at the moment, we have about 6 more questions, so I think we can meet that time frame. Okay, our next question comes from John Fleming from the Center for Biological Diversity. His question is, with the Gillespie et al. 2019 study, is there any evidence to suggest migration of produced water outside of Lost Hills or Bell Ridge oil field boundaries? Does the influence of disposal ponds, disposal injection on groundwater salinity in the Lost Hills Bell Ridge area suggest that the migration of other constituents often found in produced water, such as VOCs, chemical additives, to groundwater resources?
This is Jan. I can address some of that. As far as migration of produced water outside the oil field boundaries, we do have seen that as shown in a couple of the slides with respect to the ponds. I think that it was also shown on Lindsey's AEM studies. As far as VOCs or chemical additives, the techniques that I use to map salinities or produced water cannot detect things like VOCs or chemical additives. They can only look at changes in salinity.
Can I just, this is Matt Landon, can I just add one brief note?
Sure.
Which is with respect to looking at the effects from produced water disposal injection. Once you get away from the injection wells, there's very few water wells at depth in the Tulare Formation. So there basically are not wells available to collect more detailed chemical samples from the deep zones where injection occurs.
Thank you so much.
I think that's the next question. So I think we've answered that.
Oh.
So the next question comes from Catherine Moore. She's from the Senate Natural Resources and Water Committee. Her question is, it is really interesting to see all of the progress. I appreciate the water boards organizing this annual review. Where there is evidence of saline migration in the vicinity of the waste injection wells, I am curious if this migration is occurring within the bounds of any applicable aquifer exemption to the extent that the presenters know.
And as Matt just, this is Jan again, as Matt just noted, the limits of our more recent or modern well data post-injection wells are mostly inside the oil field boundaries. We have wells right on the boundaries, but anything outside the oil field boundaries at this point is either too shallow or too old for us to see effects in the deeper aquifers outside the boundaries.
Thank you. So the next question comes from Kathleen Gens. And her question is, how will the general public in California benefit from the results of these studies?
Hi, this is John Borkovich. I'm the Groundwater Monitoring Section Chief at the State Water Resources Control Board. And thank you for your question. I think that the intent of the legislation that enabled this work to be done is the concern about water quality in adjacent to areas where there is oil production. So the benefit is that the data that has been presented today, as well as data that has been collected by oil field operators, is made publicly available. And so those that information is stored in a publicly located our GeoTracker system, as well as within the context of any reporting, interpretive reports or otherwise, that the U.S. Geological Survey collects. So that's what we're doing. It's the charge of our program, and we're making that information publicly available.
Thank you, John. Our next question comes from Carol Hawley. Her question, well, I'll read her question. She says, my question is, has there been any discussion about prioritizing study areas by types of water usage? In other words, prioritize those areas where oil and gas production is relatively prolific and where significant numbers of the public depend upon nearby water wells for domestic water. For example, in Upper Ojai, there is a significant oil and gas production with infrastructure that is as much as 120 years old, and most of the population depends upon individual domestic water wells because there are no public water agencies that provide domestic water to us.
Hi, this is John again, and thanks again for your question, Carol. I believe we've spoken in the past, and in particular, you know, the structure of these studies that the USGS has been undertaking. One of the initial steps of the program was to look at areas of the state that had oil production and overlay that with proximity of water supply wells. So that has been done, and that's an initial step of how the prioritization scheme was drawn up in the first place. And I understand your concern about the effect on domestic well water. You know, like at the last question asked with respect to water quality and concerns about those are very important to the water boards, of course. That's our responsibility. And however, you know, domestic well users in the state are responsible for maintaining the quality of their wells and testing it. It is not something that is regulated in statute in California as far as water quality is concerned, but there is a significant population in the state that are reliant on domestic well water. Estimates range in or around 1 million or so individuals, less than 2% of the population. I misspoke there as far as the number of wells is less than 1 million. But anyway, that's something that we are interested in. And if there are data that are collected in and around these areas, they're made public. And
thanks very much, John. It is 3:30. For those of you that need to log off, please know that this recording will be made available. So for those of you that can continue, we only have 2 more. We have 1 question, 1 comment, and then we can wrap up. So if you want to hang on, that would be great. So our next question comes from Christine Zimmerman. She's from Western State Petroleum Association. And her question is, how can we get answers to questions that are not addressed during this 35-minute Q&A session? Will USGS and the State Water Board respond in writing to these questions, both addressed and unaddressed? What is the process for addressing follow-up questions, if any? When can we expect a response? WSPA appreciates the opportunity to engage on this very important work.
Thank you, Christine, for that question. This is John again. And actually, that was part of my closing comments that are coming up here after this next question, is that we'll have staff monitoring the email address for questions after the conclusion of this meeting and periodically in the days to come. If we do receive any additional questions from folks, we will address those on a case-by-case basis with those individuals that have asked those questions. And this webinar is being recorded and will be posted on our website for future reference.
Thank you, John. And the final portion of this session, it consists of a comment, and that is a comment received from Jesse Marquez from the Coalition for a Safe Environment, and his comment is as follows. There is no public reporting of the directions and depths of their drilling, the proximity to aquifers and chemicals they may be using to extract oil. To my knowledge, they do not submit a detailed drilling plan and a monitoring plan, since I have never received a public notice or a public hearing notice. Warren E&P is drilling over 200 new oil wells and reopening abandoned oil wells and using horizontal slant drilling. Warren E&P was already cited for operating in illegal and unpermitted flare combustion units. There are already thousands of operating and abandoned oil wells. There are also miles of underground pipelines. We are concerned that without a maximum limit, underground drilling will undermine the ground substructure and adjacent aquifers. Wilmington is a coastal community and there is a significant liquefaction concerns. A significant percentage of Wilmington is also below sea level. Wilmington is approximately 5 miles square inland and 9 miles square with Terminal Island. There are over 500 operating wells in Wilmington, including Terminal Island.
Hi, this is John. Thank you for your question, Jesse, and I can appreciate that your concern. I would recommend that you reach out to the folks in our sister agency at CalGEM, and we can provide you with contact information for the specific district, that's their southern district, of an individual that would be able to better answer your question. But we appreciate your input, and thank you for your participation today.
Thank you, John. And so at this point, we'll be closing our question and answer period. Thank you all so very much for your questions and your comments and feedback. Your participation in this process is very important to us, and we thank you for taking the time to join us virtually. To close out our workshop, I'll ask John Borkovich to say a few words.
Hi, thanks again for everybody attending today. My name is John Borkovich. I'm the Groundwater Monitoring Section Chief at the State Board. I want to say that, of course, the obvious, that it's a challenge to put on one of these seminars, let alone online or in person. But the team here has risen to the challenge, and I wanted to say thank you to our virtual team that put this together, in particular Karen Kramer and also Marina and our other OPP staff that have been instrumental in putting this presentation on today. I also wanted to thank our colleagues at the U.S. Geological Survey for their groundbreaking work. The board appreciates their expertise and objectivity. That's the direction that we've gotten from our board to continue on this fundamental and groundbreaking groundwater studies in the state of California. I also wanted to take a moment to acknowledge the ongoing cooperation from oil field operators in the state, and in particular, the comments that we've received from Western States Petroleum Association. Thank you for that. And we look forward to the continuing studies in those areas and meeting with you again in the near future. And once again, like I mentioned earlier, we will be receiving questions to as we go on through the days after this meeting to see if you have any follow-up questions you'd like for us to answer. Also, this webcast will be posted on our website for future reference. And thank you once again for your attendance, and have a good afternoon.
Thank you.